Hey everyone, and welcome to this explainer. Today we're unpacking the architectural genius of a neural network that just completely refused to become obsolete. You know, in an industry where AI models seem to age faster than milk, we're looking at a framework that essentially solved photorealistic faces for 7 years running. We're going to break down exactly how it works, why it was built the way it was, and the core structural advantages that keep it totally relevant today. All right, let's dive right in and address the elephant in the room. I know you're probably thinking it. Diffusion models completely dominate the AI landscape today. Midjourney, Stable Diffusion, they are everywhere. So why on earth does anyone still ship older generative adversarial networks technology in 2026? It feels kind of counterintuitive, right? If you've got a shiny, highly flexible new tool, why keep the old one around? Well, the crucial point here is that while diffusion models absolutely own the open domain, like if you want to generate a dog riding a skateboard on Mars, this specific StyleGAN architecture still completely dominates specialized, high-speed production environments. Think photoreal human faces, anime characters, or specific product shots. If you know exactly what category of image you are generating, this architecture offers something those massive, open-ended diffusion pipelines just can't match. To understand how it pulls this off, let's jump into Section 1, the latent space problem and how researchers untangled the wires. Imagine trying to change your TV volume, but your remote control also simultaneously changes the channel, turns off your living room lights, and opens your garage door. That is exactly how early deep convolutional GANs, or DC-GANs, functioned. The input noise, which we call the Z latent vector, controlled literally everything at once. Pose, lighting, identity, and background were all hopelessly entangled together. If you moved one dial, everything changed. The real breakthrough happened when researchers figured out how to map that Z vector into an entirely new, disentangled space called W. And the solution to that whole nightmare is W space. By creating this intermediate style space, researchers essentially gave high-level traits, like someone's pose or identity, and fine details, like the lighting or color, their own independent dials. The axes in this space are roughly orthogonal. That means you can adjust one thing without totally ruining another. You can quite literally take the high-level style from one image, mix it with the fine details of another, and perfectly swap their styles. This single change was an absolute game changer for advanced image editing. Which brings us to Section 2, the StyleGAN solution, rebuilding the generator. Let's see what is actually under the hood. So instead of feeding that noisy latent vector directly into the image generation layers like the older models did, StyleGAN passes it through an 8-layer neural network first. We call this the mapping network. It's essentially a standard dense neural network, an 8-layer, multi-layer perceptron that completely decouples the underlying latent geometry from the actual data statistics. Basically, W doesn't have to be a perfect bell curve anymore. It actually learns a shape that's adapted to the real training data. Now, if we break down the complex math of the synthesis network, it reveals this surprisingly simple repeating recipe. Once we have our W vector, the model starts with a learned constant 4x4x512 tensor. Notably, that's not random noise. From there, it scales up the resolution, applies a convolution, injects our W style, adds some noise, and then just repeats. It keeps doubling the resolution over and over, going from 4x4 pixels all the way up to a crisp 1024x1024. Step 3 of that recipe is the true secret sauce, Adaptive Instance Normalization, or ADA-IN for short. Instead of just kind of stirring the latent vector into every layer all at once, ADA-IN normalizes each individual feature map and then scales and shifts it based on the specific style data from our mapping network. So the specific style, whether that's the macro pose at lower resolutions or the micro lighting at higher resolutions, is injected cleanly into the image at every single level. And we absolutely cannot forget step 4, which is the noise. By adding this single-channel stochastic detail at each step, the model can perfectly render those randomized, highly realistic things like skin pores, freckles, or individual hair strands. And the best part? Because this noise is added entirely separately from the ADA-IN style injection, it creates all those tiny, vital imperfections without messing up the underlying global face structure. Moving on to Section 3. Evolution of StyleGAN, iterative bug fixing. Over the years, this architecture went through a rapid evolution. We're talking starting in 2019 with the original mapping network, jumping to version 2 in 2020, version 3 in 2021, all the way up to R3GAN in 2024, which, by the way, closed the quality gap to diffusion models while using 20 times fewer parameters. As we trace this history, you'll see each version aggressively targeted a very specific visual flaw. For example, if you look at early StyleGAN1 images, they often had these weird, blobby water droplet artifacts hanging out in the background or right on the faces. This happened because the ADA-in process was actually zeroing out the mean of the feature maps. Well, version 2 cleverly fixed this by introducing weight demodulation. They started scaling the convolution weights themselves instead of the activations, and it instantly killed those droplet artifacts. Then version 3 came along to tackle a really creepy effect called texture sticking. In the first two versions, if you animated the latent space to make a face turn, the textures, like beard hair or skin patterns, seemed like they were glued to the screen's pixel coordinates rather than moving naturally with the object. So StyleGAN3 utilized alias-free convolutions and windowed sync filters to literally detach the texture from the pixel grid. The result was perfect fluid smoothness in animations.
Let's look at Section 4, Real-World Use Cases, and where StyleGAN dominates today.
There's a stark divide in applications here. For photoreal human faces, face editing where you map a real photo into W-space that you can tweak it, and avatar pipelines, StyleGAN absolutely reigns supreme. You can even use it for domain adaptation from just 100 images. But for multimodal or open domain text-to-image prompts, the recommended approach is simple. Just don't. You should absolutely stick to diffusion models for that. StyleGAN is like a sniper rifle, whereas diffusion is a shotgun.
Now, for those narrow domains where StyleGAN is used, developers rely heavily on a little secret called the truncation trick, often referred to as SCI. This trick is basically the server operator's ultimate safety knob. By keeping the SCI value below 1, usually around 0.7, you are forcing the model to sample closer to the average face. You're trading away the wild, diverse outliers, but in exchange, you absolutely guarantee clean, high-quality, artifact-free results. And let me tell you, that is a total lifesaver during peak server loads. And that brings us to our final section, Section 5. Why StyleGAN still wins, the ultimate survivor treat. Let me put the speed gap in perspective for you. A standard 50-step diffusion pipeline, complete with all its heavy image decoding steps, takes about 3 seconds to generate a high-resolution image. A single-pass StyleGAN generation on a modern GPU takes under 10 milliseconds. That is a staggering 300 times difference in speed to get the exact same visual quality in a narrow domain. And that speed matters immensely for businesses. StyleGAN only requires a single forward pass. There's no complex cross-attention mechanism constantly checking text prompts against image data. Because every single request takes the exact same minimal computational effort, you don't even need complex continuous batching schedulers. You just use static batching. For avatar services, ID generation, or stock photos, its total cost of ownership is just unbeatable. Which leaves us with a pretty provocative thought to wrap up this explainer. In an industry that is totally obsessed with building the biggest, most complex, most generalized models possible, maybe being incredibly fast, highly specialized, and incredibly cheap to run is the true key to survival. When you only need to do one thing perfectly, sometimes the older, specialized tool is still the sharpest one in the shed. Definitely something to chew on the next time you hear a model called outdated. Thanks for hanging out, keep exploring, and keep focusing on those fundamentals.